Hello students, today we will talk about W test that we call Wilcoxon sign rank test. Earlier on we did discuss small samples hypothesis testing application using t-distribution. The underlying assumptions over there were n less than 30, sigma is unknown, and data are approximately normally distributed. What if in case of n less than 30, sigma is unknown? The third assumption, data are approximately normally distributed, does not hold. Then we can alternatively go for seeking if the data are approximately symmetrical. And stem and leaf is the diagrammatic representation with the help of which we can assess if the given data are approximately symmetrical or not. You can assume that right there in the exercise or in the question, you will be given an assumption regarding the behavior of the data, whether it is approximately normally distributed or approximately symmetrical. If it is approximately normally distributed under the prior two conditions, n less than 30 sigma is unknown, then we go for T procedure. But if data are approximately symmetrical as the assumption that we are given in the question, then we go for Wilcoxon sign rank test or W test simply. This is a non-parametric test. In non-parametric test computations, we do not compute mean, that is sample mean from the sample data, or standard deviation from the sample data. Instead, we look for the distance or the difference between the each value of data that we are given with its corresponding mean value. And then we take the difference, and difference for all such values that are located below the mean or that are less than the mean value relatively, we get negative signs with them. And for all the values that are located above the mean or higher than the mean or greater than the mean value, then we get those values with positive signs. So either negative signs we get or positive signs we get. What if we get a value in the data provided that is similar to the mean value exactly? So in that case, when we take the difference of the two similar values, the difference is 0. And 0 is a value that behaves at the borderline on the integer line to segregate or divide the two zones. On the right or above 0 value, positive value zone exists, and below 0 line, all values are negative. So 0 behaves like a borderline. So if we face such a situation in the data file or the data values, if in the data we are given a value exactly similar to the mean value, then we drop that value because we are unable to assign any sign to that difference. So this is what the theme of the test. Now we start with this example, question number 9.116, that is regarding the mean weight or the weight of US babies at birth. So the National Center for Health Statistics reports in Vital Statistics of the United States that the median birth weight of US babies was 7.4 pounds in 1990. A random sample of this year's births provided the following weights in pounds. So this is the data we are given, and at the first place and in the beginning we need to look at the data whether any such value that is given exactly similar to the mean or the median. So over here we are asked to test the hypothesis that can we conclude that this year median birth weight differs from that in 1990. The reference value for 1990 was given as 7.4 pounds. So our median value that we state in H naught for hypothesis testing purposes, we will take it as 7.4, and if we look at the data, second value in the first row is given similar to the mean value or median value. So we drop this value from the data there is no score. So if 14 is the sample size that we are given in the data, after dropping or reading out this observation from the data, we will be left with 13 observations. So now what we do state our H naught first. So H naught is mu with a curl sign on top of it is indicating the median sign is equal to 7.4 pounds. And we are asked for testing the hypothesis that median value differs from 7.4 pound. Then, as usual, in the next step, we will state the level of significance that we are given. For hypothesis testing, it is given as 5%. And since we are performing a two-tailed test, considering the not equal to sign given in H naught, H1, so we divide this given significance level by 2. Now the test statistic formula for this statistic or test is W is equal to sum of positive ranks. Now in the next step of critical region, look at the W table. We need to consider the row number 13 and 0.025 is the significance. And the table, W table gives us only the right tail critical value. That's 74 over here. 13th row, 0.025. 74 is the right tail critical value. So we draw the rejection region in this way. We are not interested in the fact that which shape the particular distribution follow. That's why we call non-parametric test distribution free methods as well, in which we are not interested in the shape of the distribution. Therefore, we just draw a horizontal line. We draw a vertical line on the right hand side to indicate it as a right tail test, and we draw a vertical line on the left side of this to indicate that it is a left tail test. So this is what we do. In 74 as the value as per the number of observations we are given in the data, we have identified from the table that this is the value. Now to work out the left tail critical value, we need to take help from the sum formula. Sum of first n natural numbers has this formula that S is equal to n times n plus 1 divided by 2. So that's 13 multiplied by 13 plus 1 divided by 2. 13 times 14 divided by 2. 2 times 7 is 14. And that's 91. So 91 is the sum. Now the formula is sum equals left tail critical value plus right tail critical value. If we are interested in determining left tail critical value, then left tail critical value is simply the difference between the sum and the right tail critical value. So 91 take away 74. That's 17. So 17 is the lower bound. And we state the rejection criterion or critical region as H naught would be rejected if W calculated is either less than 17 or it is greater than 17, greater than 74. Sorry. Now, what I've done to save the time, I have copied on the next page already the data. Over here, you can take notice of one thing, that 7.4 I have not written over here because we have to delete that value right there in the beginning, as it is similar to the mean value we have quoted in the null hypothesis. So the reason is same as I told you earlier, that 7.4 take away 7.4 as a mean value will give us zero difference, and zero difference cannot be assigned any sign. So X values are 8.6, 8.8, 8.2, 5.3, 9.2, 13.8, 5.6, 7.8, 6, 5.7, 11.6, 9.2, and 7.2. What we do, we take the difference, we introduce a new variable d. That is simply the difference between the x value take away mean value, or the difference between x and mu values. Mu value is 7.4. When we take the difference, these are the answers you must be getting. So I have listed all the answers for the difference. So to avoid any problem at the sign of ranking, at the time of ranking, so we need to in fact remove the signs from here, negative sign. So for this, we will take absolute values. And after taking absolute values, these would be the numbers. Okay, these are the data values. Now what we do, we have taken we have to start ranking the observations one by one. So starting with the least number, which is 0.2, I have assigned the rank 1. The next higher value is 0.4 with rank 2. Then 0.8 is the next higher value with rank 3. Then next higher value is 1.2, that is with rank 4. 1.4, you can notice, is repeated twice. And if these were two different numbers, these would have been assigned the ranks of 5 and 6. So what we do, since there is a tie in these two values, therefore we take the average of 5 and 6. Average of 5 and 6 is 5.5, and that's why we have assigned the rank of 5.5 to both. Now we go to the next higher value, and since we have used 5 and 6 as ranks already, the next higher rank would be 7, and that is assigned to 1.7. Now if we go to next higher value is 1.8, and it is repeated 3 times. See, this is the first one, this is the second one, and this is the third one. So what we do in that case, if these three were different, we would have assigned the ranks to these numbers as 8, 9, and 10. So we take the average of 8, 9, and 10. The average of 8, 9, 10 is 9. So we have assigned, therefore we have assigned 9 rank to all these three numbers. The next higher rank would be 11. 11 we have assigned 2.1. The next higher value is 4.4. We have assigned the rank of 12 to it. And then the highest value is 6.4 with the rank 13. So this is how we rank the data. Now what we do, I'm going to mark a tick across each value for which the difference was positive. So these three numbers we have selected. Then skip the fourth one because this has the negative sign at the stage of taking difference. So this will mark a tick across this, then this one, then this one, and then this one. So this is how we do it. And now adding them all would give us the sum. 4 plus 5.5 plus 3 plus 9 plus 13 plus 2 plus 5 plus 12, then plus 9 as 57.5. So 57.5 is the value of W calculated. Now we need to consider where it is falling. This value is falling between 17 and 74. So between 17 and 74 it is falling. We do not reject our H naught because it is falling in the non-rejection region, and H naught is not rejected. We write down decision accordingly, and we write down the decision as since W calculated does not fall in the rejection region, therefore H naught is not rejected. And we write down the conclusion as the test results are not statistically significant at the 0.05 significance level, and data do not provide sufficient evidence to conclude that. Now we copy and paste the statement given in the question for hypothesizing that this year's median birth weight differs from that in 1990. This is how we perform W test. That's all from